Hello everybody, my name is Peter Droogers. I'm from Wageningen in the Netherlands, and over the next half hour I would like to give you a small introduction in the WEAP model. So the title of my presentation is WEAP, Water Planning Tools to Support Water Management and Policy. And just as a very small introduction of 1 minute, what I said before, my name is Peter. I'm working for Future Water based in the Netherlands, and my key expertise is on climate change, water issues, water planning, and for the tools I use there is modeling, remote sensing, geographic information systems. Future Water has two offices, one in Wageningen and one in Cartagena in Spain. And we do a lot of projects for all kinds of clients like the World Bank, governmental organizations, river basin organizations, science foundations, etc. And we are working on a global scale, so we have projects in Europe, also projects in Africa and Latin America, but also quite a lot of projects in Asia. Now, if we are talking about modeling and modeling tools, I think it's good to start with the first question: why do we need quantitative information? And let me show just a couple of slides on why I think we need quantitative information. So I just went to the internet and I looked at the BBC News and I just found two hits on Pakistan. And on the left-hand side, you see, the big floods which happened in 2010, which are really having a devastating effect on the country. But other years there's a big drought. So it seems that we really have to manage our water resources in a better way. And this is one of my favorite slides. This is in fact a slide why I decided to become a hydrologist, a water resources specialist. This is from the International Disaster Database, which is showing the major disasters over the last 25 years. And if you look at the map, you see a lot of blue and yellow colors. And if you look at the legend, it's clear that the blue is flooding, the yellow is droughts. So people are mainly affected by water-related issues. It's not so much volcanoes or earthquakes. It's really water-related disasters which are people affecting in their normal life. So I think if we want to make the world a better world, it's important to do something on water issues. Of course, we are not only talking about the past, but we are also talking about the future. And we all know, of course, that there will be more challenges in the water sector. And one important one is, of course, that we've got a growing population, and here is just a graph derived from a World Bank study with the projections for the world population. As we all know that in about 30-40 years' time, we will get about 9 billion people, and this will even increase at the end of this century. So that will put a lot of pressure on water resources. At the same time, there are all kinds of projections that the GDP, the economy of the world, is also going to grow. Of course, we don't know exactly how much, but here are just some examples of the GDP growth. And most of the projections show a 3, 4, 5 or even 10-fold increase in economy. And of course, an increase in economy means also more demand for water. And finally, of course, there is a lot of debate on climate change, and there's in fact no doubt that climate change is going to happen. We don't know exactly to what extent, but for sure climate change will induce more extremes. So the flooding from 2010 in Pakistan and drought periods, they will be more frequent in the future. So for sure we should be prepared for the future. Now, talking about being prepared for the future, we need quantitative information. And this is one of the graphs I always like to show, why it's so essential to do something on the future. If we've got this graph and we've got the past, we've got today, we've got the future, then in fact we are only interested in the future. But of course, if we want to know something about the future, we should have a look at the past. And there will be, most likely there will be a trend, and this trend is probably going to continue in the future. And if you want to say something about past water resources, we've got all kinds of tools. We can do observations, we can monitor rainfall, we can monitor temperatures, we can do statistics. Some people even use remote sensing satellite information. But we are here today, and today we can influence the future. We can develop different policies. Let's say policy A, policy B, policy C. And based on these policies, of course, the future will be different, and hopefully the future will be better. So by having planning tools, and I call them here simulation models, we can evaluate alternatives. So in what way can we better manage our water resources? And of course, if you want to say something about the future, you should have some knowledge about the past. Now, in order to say something about future, you need models. And what you do if you are convinced that you need a model for a certain project, you go to Google and you type in hydrological model. And the main question is, of course, how many do you get? And I put here these question marks below the word hydrological model. And if you look further, then if you type in hydrological model, you will get more than 3 million results. So that means you're a little bit stuck because there are so many models, so which model is the best? And for that I often use this little figure where you see a square, and on the x-axis you see the amount of physical detail you want to include in your study. And on the y-axis the spatial scale, so whether you're working at field scale or irrigation system scale, basin scale, or even continental scale. And of course, if you're working at continental scale, you cannot include all your physical details, so therefore there's a kind of triangle of an area where you actually can work. Now, based on that, you can put in some dots where your questions are, and then you can fill out some of the models that can be used for answering your questions. So sometimes people ask me, what is the best model? And in fact, the answer is, the best model does not exist. It depends a little bit on the application, on the question you would like to answer. During this presentation, I would like to concentrate on one of these modeling tools which are very strong, and that's the WEAP model, which is located somewhere here. So if your problem you want to study is somewhere at system, basin scale, then the WEAP model is probably the best model to use. Of course, there are other points which determine what is the best model. So what I said, the spatial scale, the physical detail is important, but also what kind of processes you would like to include. Sometimes glacier snow processes are very important. Water quality might be an important aspect. Of course, also whether you can get support from the developers. And of course, whether the model is for free or whether you have to pay something for that. Now let's start with just a couple of slides on how the WEAP model looks like. And then later we go to a practical example on what you can do with WEAP. So the concepts of WEAP. I think WEAP is very, very strong because it's an integrated water resources planning system. It's very user-friendly and it has a GIS-based graphical interface, which I will explain later on. Also, one of the strengths of WEAP is you can build a very simple, a very basic model, but if you want to include more processes, if your study is more advanced, you can also use WEAP. Another particular strength of WEAP is, and I also will demonstrate that later, is that it's very easy to do scenario analysis. So what is going to happen if you take a certain decision? There is also a component on doing a financial benefit cost analysis, and very important is that WEAP can be linked very easily to spreadsheets or to other models. And this is just a small list of typical examples for which WEAP has been used over the past. So it's very strong in doing water allocations between different sectors. So it might be to allocate water between urban, industry, irrigation, environment. It's also very often used to work on groundwater issues. A very strong point of WEAP is you can use it for checking your reservoir operations. That's something I will explain later. Hydropower can be even evaluated by the WEAP model. And of course, a very important and hot topic is the impact of climate change can be evaluated. Now, how does the WEAP model look like? What I mentioned before, it's a very user-friendly interface, and this is just the example of how the WEAP model looks like if you start it up. WEAP is also particularly strong in looking at results and looking at different scenarios. And I just put here one typical output graph where you see the groundwater storage in a particular area over a period of 10 years in this graph. And you see here all kinds of different scenarios. For the moment, it's not so relevant what these scenarios are, but it's important to realize that the reference is in fact the case as it is today. So we are not doing anything, and what happens with the groundwater storage, it's really depleting. If you take several measures, you can restore some of this groundwater depletion. So the integrated measures, which are shown here in green, they are very, very effective in restoring your groundwater. So details are here not important, but it's just important to realize how easy it is to do scenario analysis and to get your results of your scenarios in the WEAP model. Another typical example of output which is generated by WEAP is just looking at your entire water balance. So in order to understand the system, a water system, it's important to realize what's happening in terms of processes. So this is another example of another study where you see for one particular year, for the month, January till December, all the components of the water balance. So very clear, of course, what's input is precipitation in blue and irrigation in yellow. And what is happening with that input, most of that is of course used for evapotranspiration by crops. And in this typical example, you clearly can see that there are some months where the evaporation is very high, so you need a lot of irrigation. Also interesting to see of this example is that the surface runoff in dark green is relatively low, but maybe you can look for some features to make it even somewhat smaller. So another example of what WEAP can offer in terms of outputs. This is the final example of an output. Instead of having all kinds of graphs and numbers, you can also create maps which are showing output. In this example, you see the demand for different cities and different flows, and the size of the arrows show how much flow there is. And you can even show it in a kind of moving graph, which will be explored later. And what I said before, WEAP can be very simple, but it can be also very, very complex. So this is a typical example of a complex WEAP model which was developed for the Sacramento region in the US, in California. Okay, now let's go for a more structured setup if you want to develop your WEAP model. First we do a kind of example on PowerPoint, and then I will start up WEAP and we will do a real life example. So if you open WEAP, it's important to realize that you've got some different screens, and the most important screen is the schematic view. The schematic view shows you in a kind of GIS environment your entire model environment. Once you've finished your schematic view, once you've put in all your demand sides, your supply, your rivers, your groundwater, your reservoirs, etc., you have to feed the model with some data. So you go to the next page of the model where you can input some data. And data, you have to think about the capacity of your reservoir, the area which is irrigated, the number of people who are living in the town, the climate as it is at the moment or in the future, whether what kind of crop there are, whether they are irrigated or non-irrigated. All this kind of information is needed by the model. Once you've put all this data into the model, you can press the next button, which is the result button. And here probably you remember this graph. This is just one of the results where you see the groundwater storage for a couple of interventions, a couple of measures, a couple of adaptation strategies. And the last graph which can be shown is what is called overviews in WEAP, where instead of having only one result, one graph, you can create graphs by yourself, whatever you like, which is very useful if you've got discussions with decision makers, because it's of course not only the groundwater, but you also should look at environmental flows, at urban flows. All the flows can be shown here integrated. Okay, so that was a very brief and theoretical introduction in WEAP, and now I want to go to a concrete study. And I selected a study which we are doing at the moment in Mozambique, because this case study is so typical for a lot of areas, whether you're in Pakistan or somewhere else. This is a basin where people are affected by flooding as well as by droughts. And the government asked us to support them in developing this WEAP so they can select some interventions and to explore what will be the impact on these interventions on water supply and water shortages. If you're not completely familiar with Mozambique, so it's a country in Eastern Africa, Southeastern Africa. The capital is Maputo, which is in the south, and our study is on a basin which is called the Pungwe Basin, which is in the central side of Mozambique. And here you see a little bit detail, and it's kind of a typical basin where you've got a big town here which is called Beira with a lot of demand. There's a lot of irrigation here downstream, and upstream there is some rain-fed, some forest and some mountains. So typical example of basins you can find everywhere. So we took data and we put it in our model. And here you see a screenshot of the WEAP model. This is just the land cover and the major rivers. If you look at the digital elevation model, what I said before, there are mountain areas here. There's a smaller mountain here, and here are the flat lands where you've got a lot of irrigation. And again here, Beira, which is also consuming a lot of water. So after a couple of weeks of work, we've developed this entire Pungwe WEAP model, which is shown here. It's a little bit complex. We've got all kinds of sub-catchments, we've got demand sides, we've got supply sides, and I will present them later to you. I think it's important just to briefly summarize what kind of input data is needed in general for the WEAP model to get it running. First of all, you need to have some information about the catchments. So that means you should know the area, the land cover, whether it's forest, whether it's rain-fed, whether it's shrub, bare soil, etc. You need to have some climate information, and of course the most important one is the precipitation and the evaporation. In fact, I should say the potential evaporation. Some information about soils. Of course, you need to know something about the demand, so you need to know population, you need to know something about the industrial activities. Important, of course, is the irrigation extent, the hectares of irrigation. And not essential, but for validation it might be very useful to have also some stream flow data. Now, sometimes people ask me, how much data do we actually need? And the answer is a little bit difficult, because the better your data, the more accurate your data, the better your model will be. But even if you've got some limited amount of data, you can do already some analysis in WEAP. So just remember, more data will give you a better model, but even with limited data sets, you can do something. This is just one example for this river basin in Mozambique. Here is a typical example of stream flow, how much water is flowing at various locations in the basin. And here I plotted just for a historic year in 2005. Also, it's very important, of course, to understand all the processes. So you see here a typical example of all the water balance for the entire basin. So you've got precipitation here in pink, and you've got, of course, the changes in soil moisture, you've got some surface runoff, you've got some base flow. So all these components are included in the output of the model. It really helps you to better understand. And the last example I want to show of output is something on evaporation. If we are talking about irrigation, then of course it's very important to have sufficient water available for the evaporation from your crops. And normally we express that as the demand, the potential, the ET potential, so the demand of the crops. And if you see here for one particular year in the wet season, the demand is somewhat lower, and in the hot season it's somewhat higher. And then the ET potential is input, and then the model is calculating the actual evapotranspiration. And clearly what you can see here is this actual evapotranspiration is much lower than the potential. So this indicates already that there is quite some water shortage in the basin, especially if you look at the end of the year, October, November, December, when the demand is very high, the actual evapotranspiration is much lower. Okay, now what I would like to do, I would like to start up WEAP, and I want to go with you to do just one or two scenario analysis. So let me start up WEAP here. So this is an overview of this WEAP model in Mozambique. And what I said, we've got a couple of catchments. We've got in fact 12 catchments. Here is one catchment, here is another catchment. And if I zoom in here, then what you see is one particular catchment, and I just have given this a number. And within this catchment, you've got a catchment site, as it's mentioned in WEAP, where you've got rainfall, where you've got evaporation, but in fact this catchment is generating runoff. This runoff is coming into your river, and what's happening with this runoff, it can be used by cities which are located here. So this is a kind of simplified catchment. If I go a little bit more downstream, there will be a more complex catchment, because here are a lot of activities. So you see here a catchment where you've got here the catchment itself. There is a big irrigation system which is requiring a lot of water. There are all kinds of cities located here which are also abstracting water. Here is the big city of Beira, which is also consuming a lot of water. And there is an environmental flow requirement, which is also indicated here. Now, given time constraints, we cannot go through the entire model, but what I would like to do, I just want to share with you how to go to results. So remember, in WEAP, you've got here schematic, you've got here data, and you've got results. So I will just press the results button, and let's have a look what kind of results we got. In the beginning, if you start working with WEAP, it's a little bit complex because there are so many options you can select from. In fact, it's important to start here at the top, where you can have an output results on all kinds of different issues. You can have a look at water demands, you can have a look at supplies, you can have a look at the catchments, what kind of processes are happening at the catchments, water quality can be included. also important by supplies. You can have a look at groundwater, at reservoir, etc. But let's concentrate for the moment at the demand, and let's focus on the water demand. So how much water is required for this entire basin? And I prefer to use not a line graph but a bar graph. And in fact what you see here is the water demand in million cubic meters for just 5 selected years. Now clearly you can see that the total demand for the entire area is about 340 million cubic meter. Now the question is of course whether there is sufficient water to meet that demand. And in WEAP we call that unmet demand. So remember the demand is about 340 million cubic meter. And let's have a look at the unmet demand, and again I will plot it as a bar. There is quite some water shortage, as you see. So of the about 300 million cubic meter of water which was needed, about 100 million cubic meter was not delivered in 2005. And in 2004, about 70 million cubic meter was not delivered. So apparently there is a big water shortage. However, at the same time, we know that there is also quite some outflow from the basin. So apparently there might be an option to build a reservoir. At the moment there's no single reservoir. And include that reservoir to make sure that you can store some of that water. Now that seems to be of course a very complex question. Building a reservoir requires a big study, etc., etc. But before you start with such a complex study, it might be useful to do a quick analysis using WEAP. So let's build a reservoir. And I will show you that it goes very quickly in WEAP. So we go back to schematic. And let me show the entire screen. And there is a simple trick in WEAP where you say, I want to compare two scenarios. I will do it a little bit quickly, but in fact you go to area and you say scenarios. And the entire idea is that you say, I want to evaluate another scenario. And let's call the scenario reservoir. And let's create a reservoir of 50 million cubic meters. Okay. Now we have to identify in this map where the reservoir might be built. So I just go here to the left screen and I'm just going to create a reservoir on the main river and I just place it somewhere here. Then WEAP is asking for the name of the reservoir and I just call it reservoir 1 and I say finish. And this is how you build a reservoir in WEAP. So now we've got a reservoir built. Of course the only thing we have to provide is what will be the capacity of the reservoir. So in WEAP that's very easy. You go to the reservoir, you press your right mouse button and you say edit data and you say what is the storage capacity of the reservoir. You have to identify when the reservoir will be operational, so let's say 2001. So we've defined this new reservoir and what you have to provide as input to the WEAP model, you have to provide the capacity, the storage capacity. So what I said, let's explore what will happen if we build a reservoir with a capacity of 50 million cubic meter. So the only thing you have to do is to type in 50 million cubic meter. We also need a volume elevation curve, so we can just put some numbers and later we can do it more realistic. And once you've done that, you go back to results. And WEAP is asking, oh, you've made some new input data. Do you want to recalculate? Yes, we want to recalculate. Also notice that WEAP is very fast in doing its calculations. And here we've got some interesting results. Let's first go back to the demand. and I prefer to put it as graphs, as bars. Of course, there will be hardly any changes in demand because we didn't change anything. But interesting is to have a look at the unmet demand. And again, I plot it as bars. And you see something interesting. Remember, here was the unmet demand in blue, what we just saw 2 minutes ago, for the current situation without reservoir. And if you are building your reservoir, your unmet demand, your water shortage, is somewhat smaller. But apparently the impact of this particular reservoir is not very big. The question is, of course, maybe this 15 million cubic meter of reservoir storage is not sufficient. So let's create very quickly another one where we just say, what happens if we build a reservoir with a storage capacity of 500 million cubic meter? So we go back to schematic, we go back to manage scenarios, and we create a new scenario, and I will call that scenario reservoir 500 million cubic meters. Okay. Then of course I have to go to data and I have to enter this 500 million cubic meters. So I go to data and I say storage capacity. So the reservoir is active in 2002 and the storage capacity of this reservoir, in fact it's the same but we increase it by a factor of 10, is 500 million cubic meters. And of course the same, we go back to results and we are going to recalculate, and you would not be surprised that this will have a major impact. So in fact what you see here in dark blue, you see the current situation without reservoir. You see in light green or light blue, you see the reservoir which was first evaluated with a capacity of 50 million cubic meter. And look here, if your reservoir will be 500 million cubic meter, your water shortage is even going down. This is just in 10 minutes a very fast example of how WEAP can be used to evaluate scenarios. Of course, there are 10, 20, 100 other scenarios that can be evaluated. And WEAP is very useful in sitting together with policymakers who are coming up with scenarios to overcome water shortage or flooding or whatever you're working on. And within a couple of hours you can just analyze the impact of a couple of interventions. Okay, I think we are running out of time, so I'm going back to the presentation. And I would like to have some final conclusions from this short presentation. I think over the last half hour, I discussed why it's so important to have quantitative information. And I think it's good to make a distinction between whether you're looking for strategic decision support or whether operational decision support system. And WEAP can be used for both, although its particular strength is in the strategic decision support systems. We also discussed that there are many existing models, and for particular some cases WEAP is very strong, especially if you're talking about water allocation, strategic decision making and scenario analysis. Now I've been working for more than 15 years with WEAP, which was developed in the US by the Stockholm Environment Institute. And over the last 15 years, many improvement has been made to the model. And I'm very happy to use it because it's freely available, but also the documentation is very good in means of tutorials and manuals, but also many examples exist already. And with this, I would like to thank you for your attention. Goodbye.